Welcome! My name is Nicholas Phua. I am the Capstone team lead for the Wildfire Digital Twin project.
I am also a team captain. My name is Gustavo Cotom-Lopez.
I am joined by my wonderful team. Wildfire Digital Twin is a research-driven interactive web platform that combines high-resolution wildfire simulations with AI forecasts, enabling users to visualize fire spread, weather conditions, and model predictions through an accessible online interface.
Hi, I'm Robert, one of the members of the S-Fire team. This is a demo of the Palisades wildfire simulation. This fire started on January 7th, 2025, around the Santa Monica and Malibu area of California. It wasn't fully contained until January 31st. Over those 24 days, this wildfire became California's third most destructive, with 6,837 structures destroyed. Using WRF-XPy, we were able to take the simulation outputs and process them to give us visualizations over time for things like wind vectors, wind speed, fire area, and smoke. Let's select fire area and smoke and play the simulation. So even though the part of the simulation being shown only covers 9 hours from 8 a.m. to 6 p.m. on the first day, you can still see the very rapid spread and how it started spreading eastward, which is true for how the fire did in real life.
Hi there, my name is Catherine Nemec, and I'm a member of the website development team in Professor Safa Mote's Wildfire Lab. Today I'm going to show you our simulation visualization tool. So I've got it open here, and I have a example simulation used for development right here, and I'll open that. And you can see we have a pop-up window here which is showing some ground truth data for this particular wildfire. And that can be used to compare against our simulation results. So this helps provide a ground truth reference parameter for the simulation work that we're doing. WRF-XWeb is an open source project, so I was able to contribute several improvements to the back end, including adding these images and associating those with each simulation.
Hello, this is Dinh from the website team. I'll be presenting the static website portion of our Capstone project. And the front page is just a quick introduction about our project and some current successful predictions. And we have added a navigation bar with 8 subpages here. The first one is the project description, which is just the front page itself. The second one is the team members, which introduces our mentor, Dr. Safa Mote, and the full team. The next tabs will be just showcasing our work and the technology we use. The first one is the climate models overview. The next one is the wildfire simulations. And this fire model update will be just like a block style page for updates from Dr. Mote and the future teams. The sources page will be just a reference list of all materials and resources we use.
Wildfires are not just a natural hazard, they are a growing, deadly crisis. Every year, hundreds of lives are lost, and even more people suffer serious health issues from smoke exposure. Entire communities are displaced, wildlife habitats are destroyed, and valuable agricultural and forest lands is lost. Here in the western United States, we experience the highest acreage burn per square mile. Wildfires are becoming a more frequent and severe issue. Burn areas have spiked since 2000 from hotter, drier conditions. This underscores the need for more advanced forecasting tools. Our goal with Wildfire Digital Twin is to create a tool that can forecast wildfire spread, so that decision makers can make better informed decisions and communities can better prepare for possible wildfire damages in the future.
The tool will be most useful to a number of agencies, such as local utility companies like PGE, researchers who are interested in wildfire physics and taking a look at our findings, federal and state agencies, insurance companies, farmers, anybody who's curious about wildfires, and taking a look at our modeling tools that we use to create highcasts of how they they may look like and how past wildfires look like. On our static website, we placed our research findings, and anything that's relevant to this project will all be published there. We also have a weather modeling AI, which is designed to model wildfire behavior. Each component was worked on by a different team, usually made up of 1 or 2 members or more. We held weekly meetings to share daily progress. At those meetings, we also took time to understand the goals and concepts behind each component, as quite frankly, the team would get lost if that didn't happen. Any blocks or any challenges that any team may have was discussed and tackled during these meetings. The sponsor was present at all meetings to help clarify and provide feedback.
My name is Harrison Moore, and I was a part of the S-Fire team in charge of running the dynamical model to produce our simulations, and I will be talking about how the dynamical model we used works. So we used the dynamical model known as WRF S-Fire. WRF S-Fire is a coupled atmosphere fire model that combines the weather research and forecasting model WRF with the wildland fire spread model S-Fire. Its purpose is to simulate the two-way dynamic interaction between wildfires and the atmosphere. The two-way interaction enables realistic modeling of fire behavior and its influence on weather, and vice versa. We have a diagram here showing how WRF and S-Fire work together to create the dynamical model. The diagram shows how the atmospheric model WRF and fire spread model S-Fire work together and feed off of each other to produce the simulations.
Here we have a flow diagram for our process to create these wildfire simulations. First, we research what we can about the fire. We figure out where it started, when it started and ended, and how large the fire got. Then using the research we performed, we fill out a job JSON with those details. The user then manually submits an SBatch job for the simulation. The forecast script is called with our job JSON, and the simulation details is parsed by WRF-XPy. WRF-XPy will start with data acquisition. This will obtain our weather observations for the simulation, such as grid data, satellite data, and geogrid data. Next, WRF-XPy will utilize several WPS executables for initializing the start of the simulation with our observations. After initialization, the simulation starts with the WRF executable. While the simulation is running, WRF-XPy monitors the progress and performs post-processing on the completed outputs.
Our wildfire AI modeling tool is based off of NVIDIA's ForecastNet, which is a weather prediction model. We trained ForecastNet to recognize and model wildfire behavior using simulation data that was provided by the dynamically modeling team. The simulation data consisted of a sample data run produced by the WRF S-Fire dynamical modeling tool.
Hi, this is Max talking a little about Hugo. One requested feature from our sponsor was that the static site be maintainable without any HTML knowledge. To do this, we used Hugo. Hugo is a static site generator and is used to make our site. We as a team chose it because someone on the team had experience with it. The pages themselves are written in Markdown, allowing our sponsor to edit the site comfortably. We also developed a custom theme for our sponsor, as per his requests on design.
Hi, I'm Ethel, and I was partially responsible for the development operations for the project. We used Notion under a free grant to keep everyone on the same page and had meetings every week to stay on top of that. And we also use GitHub organizations to manage all of our repositories and ownership of them under one roof, so they can be passed off to another team in the future. And we work with the Orca team quite a bit to manage access to our shared directory and also to understand the resources. I was also responsible for the data intake. I downloaded data from a variety of sources for use in our project. We wrote bespoke Slurm scripts to get things from different sources with different methods and just to make sure all of the data could be accessed. And if you're not fully aware of how Slurm works, here's a quick diagram. Basically, all of the tasks that we would run went through the middleman of Slurm, which was able to spread out all of the tasks across all of the different computers that are in the cluster.
Hello there, my name is Ahmed. For the development process, data pre-processing, we trained our AI with different types of data, each of which we believe will provide us with accurate predictions. For the forecasting data, the data consists of 5.3 terabytes of training data, and 290 gigabytes of testing data. As for the process, in terms of governing the data, it was pre-done. We also used Meta 2 pre-analysis datasets, and the data consisted of 3.7 terabytes and 1.2 terabytes of data. For the process, we needed to convert NC4 files to H5. For the Meta 2 data conversion, since each year consists of multiple NC4 files, we converted all the following NC4 files to one H5 file for the respective year. As a result, we got 8.5 terabytes of data and 1.9 terabytes of data. As for our wildfire training data, we are using the demo wildfire data to train our AI model predictions. For the preparations, since the NC file consists of variables of different dimensions, we need to have two H5 files, one of which represents small data sets and one of which large data sets. As a result, we were able to train our AI model with wildfire training data.
Hi everyone, I'm Vivi, and I work on data preprocessing and file conversion for the Wildfire AI model. One of the challenges we ran into during training was handling the raw simulation files. Most of our data came in netctf format, which is commonly used in wildfire and weather simulations like wildfire. It's great for storing multi-dimensional data like time, latitude, and longitude, but it's not made for AI training. netctf is slow to load, harder to batch, and doesn't work well with the machine learning frameworks like PyTorch. To fix this, we converted all of our .nc files into .h5 format. HTF5 is optimized for performance. It supports fast I/O, compression, and works natively with machine learning tools. The diagram here shows how we move from netctf to HTF5 through preprocessing. So why convert? netctf is great for simulation, but not for training. It's slow, complex, and doesn't fit well into GPU pipelines. HDF5 solves that. It let us batch data, load it faster, and use it directly in PyTorch without converting. Training would be much slower and less efficient. So this step is really what makes AI training possible on Orca.
The responsibilities and contributions for the whole team were split up into four major teams. The first being the website team, which consisted of Nicholas, Catherine, Dinh, and Max. They made sure that the website was running as it should, showcasing our research and any of the hindcasts that we created. They were also responsible for maintaining the website, making sure all of the content was showcased properly. The documentation and DevOps fell onto the hands of Ethel. She was responsible for the retrieval and management of all relevant data that was used on all of the tools for this project. She was also great at assisting other team members with using the Orca cluster for development and tooling, and maintained project documentation for everything. The dynamic modeling team was made up of Harrison and Robert. They aided in the research and containment of the WRF S-Fire models, produced the simulations that were visualized in our dynamic website, and was responsible for integrating the WRF X Web tool to the website. Their simulations also aided the AI modeling team with training ForecastNet to recognize a model wildfire behavior. The AI modeling team was composed of myself, Vivi, and Ahmed. Vivi was responsible for handling the data conversion that was needed since we were using two different models. One model's data was going to be used for the training of another. We needed to handle the data conversion and the pre-processing needed for training. Ahmed created some scripts and ran the training and testing and validation of the wildfire data for ForecastNet, and also assisted with data visualization.
While working, we ran into some unexpected events. Scheduling. Many members were simultaneously working on additional school courses and employment throughout the project. Due to the amount of people, we found it challenging to organize larger meetings. We found a solution in having multiple meetings a week for those who cannot make it. Lack of preserved resources. We found difficulties in finding resources for the project, mostly from data not being tracked or being removed altogether. For example, the resources for the display feature, WRF Web, had been taken offline, leading to some difficulties in operating it. Hosting. A dynamic portion of the website, the WharfX web module, needed to be hosted somewhere. This required renting an AWS instance. We managed to stay within the free tier, but full-time deployment will cost. Group split. During our planning phase, a section of our team decided to split off and do their own project, feeling uncertain with how the planning was proceeding. In response, we were forced to scale back on what we could potentially do.
Are the unexpected events of the Wharf S-Fire development. For data issues with Canada and Hawaii, we had issues with the retrieval of weather data for simulations of 2023 Canada fires and 2023 Maui fires, since they were both not in the mainland United States. For the simulations showing the ocean burning, we had issues with our simulations for the Palisades fire, showing the oceans getting burnt with no real explanation or errors indicating why this was happening. And because of this, we reached out to the WharfXPy and Wharf S-Fire developers, but they were on vacation or either sabbatical, so we were unable to get help from them. And then the most up-to-date WharfXPy repository wasn't publicly available, and then multiple custom WharfXPy modules that would improve the fire simulation accuracy were not available due to maintenance being done on them.
Forecasting wildfires is quite challenging for multiple reasons. Wildfire physics is not well resolved, especially at macro scales. There is mismatch in both spatial and temporal scales between atmospheric models and wildfire models. And the computational cost to run wildfire models is enormous. So this Capstone project was indeed a project for PhD students or postdocs. So I'm impressed with the accomplishments of our team of undergraduate students. The dynamical modeling team worked on simulations using a state-of-the-art atmospheric plus wildfire model, namely Wharf S-Fire. They were able to install this model on the Orca supercomputer cluster at Portland State, and they were able to run successful simulations. The website team did a nice job designing a static website using Hugo. They also adapted WharfX Web for our dynamic website. The AI team worked hard to learn NVIDIA's ForecastNet model, and they were able to replicate weather forecast. They also attempted to train ForecastNet using the outputs from Wharf S-Fire dynamical model. Finally, finding high-quality wildfire observations is quite challenging. Our data team was able to search for and acquire large volumes of reanalysis weather observations or weather data, as well as a reasonable amount of wildfire observations. So congratulations to our team.
As we approach the end of our presentation, we'd like to take the time to acknowledge some of our funding sources, including NASA's Wildfire Sense Research Grants for the Wildfire Digital Twin and the Earth and Science and Technology Office, the National Science Foundation Computation Award for the Orca cluster, the supercomputer that helped us run most of our operations, and then Notion, which was our way of delegating tasks and meeting notes. We were given free access for our group. We had plenty of lessons learned for this project. One of them being that just because we have a large team doesn't necessarily make things easier, especially when it comes to clarifying project features and task management. So Danskin really helped us clarify many of those features that we needed to do and the deliverables for this project. It is a good idea to maintain a project board and a schedule to keep track of every team's progress for every component. This would help in all of our weekly meetings to get a good idea of where each component is at. Most importantly, we found out the hard way that it is important that all team members understand the nature of the project and what the deliverables were. We were kind of in a hiccup at the beginning, but slowly and surely we were able to maintain a cohesive and straightforward development process for every single component. We would most definitely have a smaller team if we were going to do this again, and clearly outline tasks and goals.